My name is Trey, Watford. Blake Brown, Kendall, Coleman. We're going to present our rotary power transfer trainer today. Start off with, we have the problem statement and objectives. Basically, graduate with an agricultural mechanization degree. Every senior must complete their capstone project. We were chosen by Dr. Kendall Kirk to assemble a demonstration that will display how rotary power transfer, or how rotary power is transferred, and how effective it is throughout an entire system. The objectives that we have are as follows. The first one is to allow students to experience firsthand how to build chain and belt drive systems, to show the efficiency variation between belt drive system and chain drive systems, to show how gear ratios can either speed up or slow down throughout an entire system, to demonstrate efficiency losses at different points throughout a system, to see how the overall efficiency of a system is affected when a load is applied, and to have a portable model that can demonstrate these principles in the classroom and at other venues should any of the professors choose to take it somewhere. And also, we have the ability to have future expansion on this project for more groups to come. A little theory and background on this project. In AgMech 406, we learned the various principles of belt and chain drive with Dr. Kirk. A belt drive, as we all know, is less efficient than a chain drive is. This is essentially because when a chain drive is tensioned correctly, there is no slippage. Slippage is just non-existent throughout it. However, in a belt drive system, a slippage throughout the system is very much prevalent, depending on how tight the belt is, how efficient your system is, and that greatly affects the efficiency of your overall system. Belts have to be tightened to a much larger tension than a chain system does, which also causes a greater torque placed on the motor, and this also decreases efficiencies. It should be noted that no system out there is 100% efficient. Much as we may try, there's always going to be losses throughout a system. In AgMech 303, talking with Dr. Hahn, we learned how to calculate the gear ratios and how they affect shaft speed. When the driven pulley is larger than the one it is driving, an increase in speed occurs. One last thing that this trainer can demonstrate is how that works and how an alternator also works in the system. A good example that shows how alternators have to be at a certain RPM to function will be displayed in our system right here. Also, the higher the electrical demand that is placed on the system will also increase the harder, or the load that is placed on the alternator and the motor. So a little bit on our product design. The first step of our product was to find, our project was to find a suitable support system that would hold up this entire really project. We found that the Cobalt tool chest at Lowe's is what we were going to start out with and build our base upon. Even though we knew we were going to be under the capacity that the statistics show that the chest would hold, we decided to reinforce it anyway, give it a little bit of extra, support throughout the entire base, and in case for future expansion anything heavy gets put on it, it will definitely have the ability to hold that load. We decided next to add a base plate on the back that would support the alternator, the pulleys, the light system, and ultimately it's another way to give the chest more support for all that extra weight. Rather than welding it, you'll be able to see shortly, but there are bolts placed along the back side of the chest. That way, in case anyone needs to make any major modifications to it, it can be taken apart with ease rather than having to cut through welds or try and tear anything apart. Our next step that we had to figure out was finding an alternator that would fit the needs of this system. This was a challenge because the alternators we need to have to run at around 2,000 RPMs to engage, and once it engaged, the alternator can then return the power to the battery at the bottom. To ensure that we hit the 2,000 RPM mark, we machined the smallest pulley that we were able to find that would fit to fit the alternator so that the user would be able to force the speed up from the motor to the alternator. Another constraint that we faced was finding a motor that was small enough that we could carry it around to individual classrooms. Most outlets in household applications and classrooms, etc., only draw around 15 amps. And that was kind of a constraint, but we were able to work through it and able to find the motor that fit our needs.
All right, a little background on this cage you see right here. This is added to protect any users from flying pulleys and gears and chains that may fail during operation. This also supports this back plate so you don't have any wobble in it when things are getting going. We also added a safety switch on the door to be sure no one's hands were in the operation and it got accidentally turned on. You see it's located right here, right behind this door right here. The switch, this is the switch to cut it on, and this kill switch will only enable for the power to be directed from the outlet to the motor if this door is shut, or if you put your hand on it. And so in order to have the tension abilities in this back plate, we had to drill holes and take a jigsaw to it to slot it so we can tighten up the tension in from each stage. We then had to fabricate a mount for the alternator because it couldn't just sit in this back plate as it is, so we had to make this box for it, and it sits right in the box, and it is able to slot just like the other bearings. So right under here, all our wiring is hidden. As you can see, these are the front switches on the front. This switch bank is, we would have a 6-gauge wire running to our battery, and that's what powers these lights. But anyway, we have our switch, and running from here back to our power source, and also to our motor, and then from our motor up to the kill switch, and then back to the motor. This little thing right here is our conduit on the back side. We'll turn it around, you can see it. But it is 1-inch square tube, and we fabricated this conduit system, and we have all the wires coming out the back, and they run up in here and all the way around. We took a plasma cutter on the back side and just went all the way around so we could tuck the wires in there.
And here's our DC wire schematic. We've explained it before, just want to bring it up again to show how we got our what we used for right here. I mean, we initially wanted to use 8-gauge here. We found out we were going to be pushing way too much energy through it, so we went down to 2-gauge from our battery and our alternator, and to feed into this one central point to come into 8, we took a little bank here, and Kendall drew us up a blueprint, and we cut out a piece of aluminum. And what happens here is the aluminum bolts in, I don't know if you can see it, it bolts into these 8 slots right here, and it tees off each one, and then it has this little flag coming, or a little tab here, and that's where you bolt your big 3/8 in, and then each individual wire that went to each switch would come out here and go to each light. Our AC system will supply power to the motor. We ran 10-gauge wire. We initially went with 14 because based off the nameplate, our plate for our motor, it says it draws 13.2, but under load we found that it draws up to 30. So we had to step it up quite a bit. We were getting a large voltage drop. For our DC system, we went with 2-gauge wire all the way around. That alternator pumps out a huge amount of electricity. And for the lights, since it was being divided up into 8 different pieces, we were able to go with 16-gauge. All right, well, the final step for this application was to weld the 13-gauge expanded metal on for you, so you had something to stop from coming through. We went through a couple different ideas for painting this thing, and we found that the Rust-Oleum Rhino liner worked the best because it's just more durable and it looks pretty good too. So testing, got finished, everyone's real excited. We went to run our first test and we tripped the breaker in maybe 10 seconds. Flipped a couple lights on, motor just went down. We didn't know why. We thought maybe we had a short somewhere, wired something wrong. We found out that we were pulling 30 amps in, and we designed the system to pull in 13, and we were getting a voltage drop from 118 to 97. That's rather extensive. So we increased the wire size from 14 to 10, greatly reduced that, and everything's been fine so far. The test, you essentially want to read 4 things. The AC voltage and the AC amps, those are your input. And then you got your DC amps and your DC volts, and that's your output. The AC amps and volts are what's coming into the motor, and then it turns this alternator and outputs the DC amps and the DC volts. Key concept in our project is where efficiency is lost in the system. In our system, it can be lost in 3 places. What happens is the motor turns and you have efficiency lost there. Then it goes through your pulley and your drive system. That's another place efficiency is lost. And then your alternator, efficiency is lost there. So to get around that, what we did is we did a direct drive from our motor, and for our first stage we did just the alternator in this area right here, and that way we got all 3 losses in the same one. And then from that we did 1 belt drive to our alternator, so we did one extra step. And in theory, the only extra loss of efficiency should be that extra belt drive. So from that, you can calculate just the belt drive loss. Another concept that you have to pay attention to is keeping the same pulley ratio. Like Trey said, we had to machine the smallest pulley possible to go on this alternator, since our motor is only 1750 RPMs. The alternator won't kick on to 2000. So what we ended up doing was a 3.3 gear ratio. And what happens is, if you went from a different gear ratio or went to a different gear ratio, your alternator would put out more or less because the RPMs would change. And then all your data would just be skewed. It wouldn't be correct. Here's the data we got. What we did is we took a voltmeter, ammeter, we stuck it on our AC side and our DC side, and what we did is we went from 1 light to 2 lights to 3 lights all the way up to 7. We can't get the DC, or we can't get the alternator turning fast enough to power that 8th light readily. It loads the system too much and shuts down and trips breaker. The motor isn't pulling too much. So what we've got here, I'm going to show you. DC amps, DC volts, AC amps, AC volts, and all those numbers, are put in to calculate what we have over here, our DC watts and our AC watts. And as you can see, the direct drive is here, belt to belt, belt to chain. DC watts on just the direct drive, 106. On belt to belt, 122. That was outlier. The further you go down, it evens out. And then belt to chain was 85. What you really want to look at is your efficiencies. The total efficiency of this system down here at the most loaded down part was 23. Belt to belt, 19. Belt to chain, 21, which works out to be right because the belt to chain is going to be a little bit more efficient. There's no slippage. You don't have to worry about losing anything to friction. And the belt to belt should be just a little bit less efficient than the belt to chain. To calculate drive efficiency, since you have 3 places you can lose it, you've got to take your belt to belt drive and subtract it from your drive, and then you divide it back from your belt to belt. So when we did chain drive efficiency, we had 98.66 efficiency. It should be, in theory, 100%, but since the drives weigh more, the sprockets weigh more, you're going to put more work on the motor, which means your efficiencies are going to go down some. And the belt drive is 95.74. That correlates pretty much to what we learned in class. We were told to assume an efficiency of 94% for a belt drive system. And here's a chart. It displays exactly what we want it to. Here you have, as you're putting on lights, or putting on more load on the motor, you've got your direct drive is on top. You've got your belt chain right below it, and as far as belt to belt, on the last one, we lost so much power going from belt to belt that it wouldn't even power the 7th light before it placed so much load on the motor it just cut off. As far as budget, we came in under budget. We splurged a little bit on some things and cut back on some things, and we originally estimated around $1,300, and we came in just a little under $1,300. But as far as labor, we grossly underestimated how much work was going to go into this. And we completely blew that out of the water. Future work, the first stage of this project is done for us. Our advisor said he's very happy with it, but me and Mr. Blake Brown here, we're gonna stay an extra semester and further our knowledge, and we're gonna work on we're gonna put a tachometer on shafts, and we're also gonna put ammeters on it and voltmeters, and have a live feed display. And that way we won't have to sit here and do things one at a time. We'll have a live readout. You can flip a light on and immediately see the RPM change. You can see the voltage drop. And you'll be able to see all that. It'll log the data for you instead of having to do one thing at a time and punch it in Excel. It'll just be there and it'll make the graph for you.
Everybody ready for the initial demonstration? One thing that's important about this, I want y'all to listen to the strain that gets. You'll hear the whine. When you start flipping on more lights, you'll hear that motor load down. So I just want y'all to listen to the strain.
Y'all see how fast that turned off? It's got such a load trying to power all these lights that it just shuts down immediately.